Now let's take a look at temperature scales. We are already familiar with Celsius, Kelvin, and Fahrenheit. Here's the Rankine scale, named after a Scottish physicist/engineer who came up with this scale. And as the Celsius is related to Kelvin, so the Rankine is related to Fahrenheit, except it has an absolute zero is its actual 0 point. However, in science, we typically deal with the Celsius and the Kelvin scale. Okay, now one thing about the Kelvin, we know that its zero is absolute zero, and that's equal to approximately negative 273 degrees Celsius. And just as a few reference points, we have here the boiling point of helium, which is just above absolute zero at 4 Kelvin, minus 269 degrees Celsius, minus 452 degrees Fahrenheit, and 7 degrees Rankine. The boiling point of oxygen, 90 degrees Kelvin, minus 183 degrees Celsius, minus about 300 Fahrenheit, and 162 Rankine. And then here's the boiling point of mercury at around minus 39 Celsius, 234 Kelvin, minus 38 Fahrenheit, and 421 Rankine. And then, of course, we know these two very well, the melting point of water and the boiling point of water. 0 degrees Celsius, 100 degrees Celsius, 273 Kelvin, 373 Kelvin, because the degrees are exactly the same in both cases. Same with the Fahrenheit and Rankine. 32 degrees Fahrenheit for the melting point of water, 212 for its boiling point. 180 degrees difference. It doesn't look exactly like there's 180 degrees difference here. Oh well. 459 Rankine, 671 Rankine. We're not going to be using this scale, so we're just going to move on and look at our Celsius and our Kelvin. Now, one thing that is very, 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 very important to remember when we're dealing with these gas law equations is that our temperature must always, always, always be in units of kelvins. Always, always, always. Regardless of the gas law you are doing, if you are using temperature as part of an equation, it must be in Kelvin. Now, as a reminder, to get to Kelvin from Celsius, you add 273 degrees. And to get to Celsius from Kelvin, you subtract 273 from the Kelvin. Now, you may not have to use this very much, but just as a reminder, degrees Fahrenheit is 1.8 times degrees Celsius plus 32, and degrees Celsius is 0.556 or 5/9 times Fahrenheit minus 32. So always, always, always convert your Celsius to Kelvin, and if necessary, Fahrenheit to Kelvin. Okay, now we know from our everyday life that gases expand when they're heated and they contract when they're cooled. So we know there's a relationship between volume and temperature. In terms of the kinetic molecular theory, gas molecules move faster when they're heated. Therefore, they cause the forces with more force, and so there's a relationship also between pressure and temperature. Now, there's no such thing as a negative volume, and there's no such thing as a negative pressure. The smallest pressure you can have would be 0, and the smallest volume you can have would be 0. So because we're looking at the relationship between temperature and these other physical properties, we've got to have a scale where the lowest possible value is also 0. So that's why we have to use Kelvin. Celsius has a 0 point, that is the melting point of water, and it also has all these negative values. So we never, ever, ever use Celsius in our gas law math. We always convert our temperature to kelvins. Okay, now let's look at this little abbreviation here, STP. It stands for Standard Temperature and Pressure. The standard temperature and pressure means that our atmospheric pressure is 1 atm, and it means our standard temperature is 0 degrees Celsius, which we know is 273 Kelvin. So anytime you're given STP, you automatically know what the pressure is, 1 atm, and you automatically know what the temperature is, 273 Kelvin. Now, we know from our everyday experience that if a gas is heated, and here we have a balloon which is in ice water, so its temperature is about 0 degrees Celsius, and here we have a balloon above boiling water, so its temperature is going to be 100 degrees Celsius. As a gas is heated and the pressure and number of moles are kept constant, the volume is going to increase. And this is how hot air balloons float. The air inside a balloon is heated. It takes up more volume even though it has the same amount of mass, so it's less dense, and it's able to float because it becomes less dense than the surrounding air, the surrounding air is at a temperature lower than the heated gas inside the balloon. So this is what's known as Charles' law. And we know, as I said, from our everyday experience, volume is directly proportional to temperature. As one goes up, the other goes up. So as temperature increases, volume also increases. So here is the way we can express Charles' law if we're looking at an initial state and a final state. V1 over T1 equals V2 over T2. And for Charles' law to work, our pressure has to be constant and the amount of gas that we're looking at has to be constant. And these are the conditions that are met by a closed balloon. Pressure inside the balloon is always going to be atmospheric pressure, and then the number of moles of gases are going to remain the same because it's a closed system. So this is Charles' law, and as I said, as long as you remember to get your Celsius degrees to Kelvin, it's just a matter of doing simple algebra to solve for an unknown.